Good afternoon, everybody. We are the team members of TensegrityWing. My name is Robert. I am one of the team leads.
I'm Sean. I'm the structure sub-team lead.
I'm Elias. I'm one of the other team leads as well.
I'm Dennis. I'm from the aerodynamics team.
And unlike Design Build Fly, we are designing a wing design that's meant to move, but not move the way that they have showed. We are unique in that we are the first TensegrityWing project here at the University of California, Irvine. Part of this definition.
So we'll start by defining the project and the motivation of the project. So, as a lot of you know, the shape of the wing is very important for the performance of an airplane, as well as for the stability of an airplane. However, with conventional airplanes, although they do work very great, the discontinuous surface increased drag on the wing and the airplane. So our goal is to create a tensegrity wing. What is that? A tensegrity structure is a structure that's comprised of continuum bodies which are stabilized by one-dimensional mass. So our goal is to create a tensegrity tower, which will be showed later on, and to kind of put that in a wing and have our wing morph. And by doing so, we hope to decrease the total weight of the wing, decrease the drag that's reduced, and achieve more wing shape as well. So last review, we presented the top design, which is 1D members that can contract and stretch more of the shape of the wing. However, after running simulations, we realized that this was not enough for the design that we wanted. So now, this is our current design, where we have a torsional tower running along the ribs of the wing, and by twisting the tower, we can then morph the wing. And as my colleague Robert mentioned, our goal is to become the first UCI senior design project to design, manufacture, and test a morphing wing. Our objectives are to finalize our base airfoil by verifying data from Profili software, which is a airfoil modeling software that is used. So we want to verify that data with ANSYS CFD calculations. We want to determine the materials from the wing skin, the tensegrity 1D members, and the ribs. And we want to determine the actuators that are going to be used to rotate the tower, the tensegrity tower. We want to achieve a total of 10-degree twist, because the base airfoil that we chose is the Falcon airfoil, and the stall angle for that is 10 degrees. And I'll pass it on to Robert.
Project management. So we've separated ourselves into 3 base teams, sub-teams: aerodynamics, led by Elias; structures, led by Sean; and materials and electronics, led by myself. We also call it fabrication sub-team. And there are the team leads, Elias and myself. We have a documentation team lead, two documentation team leads by Elias and Fernando. And we also have a financial officer, who's also Fernando, and a safety officer, once we get down to actually building or fabricating our wing design. And our timeline, so we are pretty much on schedule. We've completed our base airfoil, and we've completed most of the testing on SolidWorks and on ANSYS with our components and with our materials. We did a lot of testing with wing skin material design, and we had to switch from last quarter when we decided to do arc-clad aluminum. But this time we're looking into foams and lighter materials that will be more feasible for shaping the airfoil as desired by our specifications. And all that's really left for this quarter is our to finish up on our ANSYS Profili data, and which is like almost complete by this point, and then our plan of fabrication, which we have settled, and all that's left is to actually buy our materials from our vendors and just start fabricating and getting our wing put together and assembled. Spring quarter will be the creation of our wing and our final testing in an air tunnel and seeing how it works. We've also guaranteed usage of the biggest wind tunnel, which is here on campus. So that's all settled. We just hope to have it work and have it operate the way we designed it. But if necessary, we'll always go back and fix it again. And so that's it. And then our final report. writing, which will be at the end of the next point. So the progress for the materials and electronics subteam. We've concluded our search on materials for our airfoil design and our material properties. So most of our materials are selected. Our wing skin material is also selected, but we still have to go through some testing to see how that works. Because there's different material designs that we have, and different vendors that have given us good options for materials. And we have collected a budget of materials of what our rough estimate of our budget is going to look like. All that's really left is just to purchase our materials and undertake the fabrication process. We also plan to create some of our own materials through 3D printing here on campus, which will be cheaper and more efficient than having to buy and wait the long process of being shipped to us. And we also have to finish coding for the motor.
So far, we obtained the average coefficient of drag and lift values for twisted airflow from 0 to 10 degrees. And the equations CL effective and CD effective are listed below. And also, we finalized our airfoil selection, and which we choose is the Falcon IL airfoil. And the equation that we use is the lowercase f function, which we use. And the constants C1, C2, and C3 are just random constants that we use to determine the best airflow characteristics. And what's next to do is verify the probability data with ANSYS flow simulation and input pressure distribution in SolidWorks. Since we'll be testing the airfoil and wind tunnel, there's like a airstream which will be going at 20 meters per second, and we need to test how that will affect the skin of the airfoil. And also there's a CFD simulation of the airfoil in ANSYS.
So the structure sub-team has finalized our SolidWorks model. We scaled it up from the previous size. Originally it was 250 millimeters in wingspan. We're taking advantage of the new larger wind tunnel, so now it's 600 millimeters in wingspan. The assembly is set up in SolidWorks, so we can just run simulations on it, static stress analysis. And that's what we're working on right now. We're trying to collect stress plots for the skin and for the ribs, so we can see how the different materials will react. Some technical approach. So our requirements, the main one is the 10 degrees of twist. We accomplish this by twisting a section of the wing a fraction of that, an equal fraction of 10 degrees. One section is from one rib to the next. We need the wing to be able to maintain its angle of twist regardless of wind influence. We also have to make sure that the skin and the ribs won't yield after they're twisted. And the wingspan is limited by the boundary layers of the wind tunnel. So what we want to do is get a tensegrity structure inside the wing. We believe this will improve aerodynamic efficiency and also reduce the overall weight. We accomplish this by taking a torsional tower design, which is the image on the left, and modifying it for use with our wing. So what we did was we replaced the large white rings with our ribs, and the rest of the structure stays relatively the same. So when we apply tension to the wires that run throughout the ribs, using a rotational motor at the fixed end, this will cause the ribs to twist and deform the airfoil.
Engineering principles. So our focus has been on stress, yield strength, material elasticity, tensegrity systems, and our aerodynamic properties. Our goal is to have our wing not fall apart, first off. And it has to maintain its shape as it twists and alters its shape. Maintain its shape in the way that it doesn't ruin any aerodynamic properties it would have if it was under flight. So our focus has been to make sure that the pressures are not too extreme on our wing design, and keeps it aloft in the air with proper lift and dynamic forces. Our material elasticity, tensegrity designs usually focus on compression and tension to provide its shape. So our concern is just how elastic the material will be. Like how will it be too tough? Will it be too tough to move, or will it be too easy to move? So that's been our main concern on our material selection. Excuse me. So that's our engineering principles.
So for a bigger picture, having a higher aerodynamic efficiency means reduce the overall weight. And in terms of an academic standpoint, having a successful prototyping and testing of the TensegrityWing means inspiring further testing and research on moving wings. And from an environmental standpoint, that means decrease in fuel consumption by decreasing the parasitic drag, the overall weight, and increase range of aerodynamic properties. And from an economic consideration, this means a decrease in flight time due to the decrease in drag, which allows the airplane to fly faster and weight. And from business consideration, this means an expansion of commercial airlines and allowing people to fly more often.
So in terms of realistic constraints, next slide. So here's just a simplified version of our budget. Total cost would be $1,311. About 44% of that goes towards purchasing the software that the aerodynamics team used. 2 licenses of the fulfilling data were purchased. We forecast that 24% of the total budget would be used for materials in the manufacturing of the actual wing. And the actual manufacturing process in terms of tools and processes, we forecast at 30% of our total budget. And the next slide will show a more detailed look at our budget. Next slide. So here's just like a more detailed look at our budget, materials that we would use, and then the software is listed up top too. So in terms of feasibility, we plan to begin purchasing the materials that we would use to build the wing by week 9. We also want a prototype of the Tensegrity Tower built by Winter Design Review, because we want to be able to showcase how our wing will actually morph. And we want to begin fabricating our official wing around the first week of 3/4, and begin testing in the air tunnel by week 6 as well. So thank you, and if there's any questions,